Hi all. So in this today's session, we will be dealing with applications and stability analysis. So if we are given with a matrix, we know how to calculate the eigenvalues, and based on the sign of eigenvalues or based on the nature of the eigenvalues, we can determine their stability. Okay. If for a particular matrix, since this is a diagonal matrix, we know the eigenvalues are -1, -2, and -3. Here you can see that here the real part of each of the eigenvalues is negative. All real part of eigenvalues is less than 0. In that case, we say that they are asymptotically stable. Okay, and if any one of the eigenvalues having a positive real value, which is, for example, in this particular matrix we have 1, so here the real part of 1 is 1 itself, so which is greater than 0. In that particular case, if any of the eigenvalue is having its real part to be positive, then it's said to be unstable. Okay, and suppose if the real part of lambda is equal to 0 just for a particular eigenvalue, since the eigenvalues they occur in conjugate pairs, for one particular eigenvalue we mean that for both the conjugate pairs, except for both the conjugate pairs, the rest of them are less than 0, and for just one, if the real part of lambda is equal to 0, then we say that they are marginally stable. Okay, and now if real part of some eigenvalue is equal to 0 with multiplicity greater than 1, what happens is they becomes unstable. Okay, for example, in this particular case you can see 0, 0 and -1. Since it's a upper triangular matrix, you can see their eigenvalues are 0, 0 and -1. So in this particular case you have two eigenvalues with the real part equal to 0. In that case it's unstable. So you just remember this: if all the real part is less than 0, then it's asymptotically stable, and if at least one of the real part is greater than 0, then it's unstable. And if real part of lambda is equal to 0 for simple only, and the rest of them are having less than 0, then it's marginally stable. And if real part of lambda is equal to 0 with multiplicity greater than 1, then we say that's unstable. Okay, now we will be dealing with a new session, principal component analysis, and in this particular area we will be dealing with problems related to PCA, which is principal component analysis, for a two variable data set. And now suppose you are given a data, so you will be given the x values 4, 8, 13, 7, and you will be given y values 11, 4, 5, 14. Okay, and now first what we do is we'll just calculate the number of observations, which is 1, 2, 3, 4. So n is equal to 4. And now we calculate the mean for x and also for y. So mean for x is 4 plus 8 plus 13 plus 7 divided by 4, which is equal to 32 by 4, which is 8. Okay, so mean of x value is equal to 8. And now in coming to y, we will be taking the mean 11 plus 4 plus 5 plus 14 divided by 4. So that is equal to 8.5. So you have the mean of x bar is equal to 8 and mean of y bar is equal to 8.5. Now we'll be constructing our table like this. So here we'll be writing xi all the x values, and here you will be writing yi's all y values. So this will be your x1, this is your x2, this is your x3, this is your x4. Okay, that's why you have the name xi. And now here you have ya, which is y1, y2, y3, y4. And now you will be calculating xi minus x bar. So for that you had x bar is equal to 8. Now under xi minus x bar you will be having 4 minus 8, which is negative 4, 8 minus 8 0, and such a way you calculate the value, then square it. Okay, similarly you calculate yi minus y bar. Y bar was 8.5, so 11 minus 8.5 is 2.5, and similarly 4 minus 8.5, calculate all the values, and then you have ya minus y bar the all square, taking the square of these terms. And then also you can do xi minus x bar into ya minus y bar. Okay, multiply these two terms and you have this. And now you need to sum three columns, which is xi minus x bar the all square, then ya minus y bar the all square, and also xi minus x bar into ya minus y bar. So you have their sum is to be equal to 42, 69 and negative 33. We'll find the values of covariance of xx. So covariance of xx is none other than 1 by n minus 1 summation I is equal to 1 to n xi minus x bar the whole square. So you had this sum to be equal to 42 and divided by n minus 1. N is equal to 4. You had 4 observations. So 4 minus 1 you will be 3, having 3. So it's 42 by 3, you have 14. And covariance of yy is you have the sum divided by 3, which is 69 by 3, which is equal to 23, and this sum divided by 3, which is equal to negative 33 by 3, is the covariance of xy. And now we'll form a particular matrix where the first entry is covariance of xx and the last entry is covariance of yy, and in between you have covariance of xy and covariance of yx. Both are the same. Okay, since yi minus y bar into xi minus x bar gives the same value, so covariance of yx and covariance of xy are the same. So you form this particular matrix by substitution. So here it's 14, here it's negative 11, here is also negative 11 and 23. Now this particular matrix is called as the covariance matrix. Now from the covariance matrix you need to calculate, this is a 2 by 2 matrix, and now we know how to calculate its eigenvalue. What we do is this matrix minus lambda I, its determinant should be equal to 0, and when doing that you have lambda square minus 37 lambda plus 201 is equal to 0, and you can solve this using the quadratic formula minus b plus 4 minus root of b square minus 4ac by 2a, and using that you get the two eigenvalues, which is 37 plus root 565 by 2 and 37 minus root 565 by 2. So the corresponding values will be lambda 1 and lambda 2 as shown here. So your first principal component is termed to be of first eigenvalue lambda 1, which is the largest one. Okay, you will be getting two eigenvalues and you should choose the eigenvalue which is the largest among, and that particular largest eigenvalue is called as the first principal component. Now after the we have the first principal component, which is the largest eigenvalue. Corresponding to that eigenvalue we find the eigenvectors. So we'll just do the matrix minus our lambda 1 minus I, so you will get a particular matrix like this, and this is the 3849. Okay, I just missed it. So it's when you do this particular matrix, to get the eigenvalue you have the matrix minus lambda 1 I into v should be equal to 0, and your v is equal to some xy, and this v is equal to xy. So substitute this and you need to find what is x and y, then you get v. Okay, for that you just multiply the first row and the first column, that is minus 16.348 x minus 11y equal to 0. Then the second row, while multiplying you have this equation, and then what you do is from the first equation take this 11y to the RHS, and then you have this equation, then do what is x is equal to you can take this value to the denominator and you have this value. And now if you are choosing this y to be 16.3849, what you can do is x will be equal to negative 11, since both the values will cancel. So you choose y is equal to this and x will be equal to this. So our v was equal to xy, so your x is 11 and your y is this value. Okay, now what you do is you just find the norm of v. So for norm of v, what you do is root of 11 square plus minus 16.3849 square. Okay, so you have that particular value is equal to 19.7349. Now you get a new normalized eigenvector. For that what you do, you have v here, this is your v, and then what you do is just divide each entry by this norm. Okay, divide 11 by 9.7349 and you have the value 0.5574, and you divide negative 6.3849 by 19.7349 and you have the value minus 0.8302. So this is your E. Using this you can find the principal components. So for that your pi is given by, you have an E matrix which is a column matrix, and just take the transpose of that, which is 0.5574 minus 0.8302. So this is your E transpose, and then you multiply for p1. What you do is you'll just take the entry x1 minus x bar, that was minus 4, and you will take the entry y1 minus y bar, which is 2.5, and you multiply this both. Okay, this column matrix and this, So this row matrix and this column matrix, when you multiply you get the value, and that is your P1. And now to get P2, what you do is you will just do E transpose into x2 minus x bar and y2 minus y bar. So you have this value, and you, in such a way, for each you had 4 entries, so you will be getting P1, P2, P3 and P4. Okay, so these are your projections of the eigenvectors. So this is called principal component analysis. In a similar way, you can also, yeah, just as a final data, you can just write the observation in the first column and then write the first principal component values in corresponding P1, P2, P3, P4 values can be written in this table as the final answer. And also you can write the first principal component, that was our eigenvalue, largest eigenvalue, and the value can also be written as the final answer. Now we'll go to a new problem where you are given with x values and you are given with y values. Okay, so you are asked to find, apply PCA and reduce the dimensions of the given data. So what you can do is, you are given with x, you are given with y, just calculate the number of observations: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So your n is equal to 10. Find x bar, find y bar. So your mean is 1.81 and 1.91. Now you will form this table. You will write all the xi entries here. You will write all yi and do xi minus x bar. That was 2.5 minus 1.81. Every entry you will be subtracting with 1.81 and you will have this value, and here it will be, you will be subtracting with 1.91 and taking the squares and calculate these values, and you will sum up which all values you need to sum. You need to sum this value xi minus x bar the whole square and this value yi minus y bar the whole square and also this value. Okay, and now after summing you have your values to be equal to 5.549, 6.449 and 5.538, and using these values you can find the covariance of xx. It was equal to this summation xi minus x bar the whole square divided by n minus 1. Here n was equal to 10, so it would be 9. So just divide and get covariance of xx. Similarly, get covariance of yy and get covariance of xy, and that will be same as covariance of yx. Now form the covariance matrix, and then you can find the eigenvalues corresponding to that particular matrix. And when you get the eigenvalues, this will be something like this. So you choose the largest eigenvalue to be of first principal component, which is 1.2840. Now corresponding to this lambda 1, we'll find the eigenvector. What we do, we'll subtract the eigenvalue from the diagonal entries and then we'll multiply by v to get the eigenvector. So we'll have a equation in this way, and just we'll find the eigenvector. So your eigenvector will be 1 and 1.084. Then normalize them. So that will be root of 1 square plus 1.084 square, and you have the value. Then you will divide each entry of v with 1.474 and you have e. Then what you do is, we'll take the transpose of this one, so that will be 0. This column will be written in the row wise, so you have E transpose, and to get P1 what you do is do E transpose, then xi minus x bar and yi minus y bar. You do this row matrix into column matrix and you have a particular entry, you get P1. In a similar way, to get P2 you have this same E, and here the entries will be x2 minus x bar and y2 minus y bar. Okay, so you find all the projections. So this will be your final answer. Now let's okay, so here we have one last session from this module. So we will be learning how to calculate the eigenvalue, eigenvector, and also how to do PCA in Python. Okay, so first you can open just your, you can log in into your Python account, and then what you can do is, we'll just see the code to calculate the eigenvalue first. So first you will have to type import numpy as np. Okay, so you are importing the dictionary numpy from Python, and then now first you will have to enter the matrix. So just write a is equal to np dot array, and you can open the bracket and just enter this matrix as shown here. And now to calculate the eigenvalues and eigenvectors, what you do is just write eigenvalues comma eigenvectors equal to np dot linalc dot eigenvalue of A. Okay, EIZ of A. And now you have already you have entered the matrix and you are asked them to find the eigenvalue and eigenvectors. Now just ask them to print eigenvalues and then print the eigenvectors. Okay, each eigenvector will be printed in the column, so just write print eigenvalues and just write print eigenvectors. Then you can run the screen, sorry, run the code, and then you will be getting the eigenvectors. And first you will be getting the eigenvalue, so that is 6.61 something and 30 point something, and also you will be having the eigenvector. So this is the eigenvector. First column is the eigenvector of first eigenvalue, second column is the eigenvector of second eigenvalue. Okay, okay, now we will also continue with finding PCA. How to do it in Python. So first you import numpy as np. Then what you do is we'll just input the x values and y values in the array. We'll just name a is equal to np dot array, and we'll enter the x value and y value shown here. And then in the second step we'll just first step is to calculate the mean, right? So just write mean is equal to np dot mean of a comma axis is equal to 0, then a centered is equal to a mean. Just write that. And then if you have the mean, what is the next step? It is to calculate the covariance matrix. So you write covariance under slash matrix is equal to np dot covariance of a under slash center dot t. And then now we have the covariance matrix. What we do, we find the eigenvalues and the eigenvectors. So for that we already know the chord eigenvalues comma eigenvectors is equal to np dot lineal dot eigenvector of the covariance matrix. Okay, in last problem we did it was a, because a was a matrix. Here you define that matrix to be covariance, sorry, cov under slash matrix. So just write it here. And then in the next step what we do is we need the largest eigenvalue. So for before that we will sort it in the descending order. Okay, so for that you have idx is equal to np dot arcsort eigenvalues, and then just do the chord as given here. And now what we will do, we'll just take the first component. Okay, since it was in the descending order, we'll need the first component, that is the largest eigenvalue. So just write k is equal to 1 and principal slash components equal to eigenvectors, and their corresponding eigenvector will be chosen. And then what we do is projected data slash data equal to np dot a centered comma principal components. So we'll get the projections of each of the datas. So what you do is we need to display the result. So just write print mean, print covariance matrix, print eigenvalues, print the eigenvectors, and print the projected data. Then after running you can see the results. Here you can see the mean. See, mean is given. Then covariance matrix is this 2 by 2 matrix, and then you are given with the eigenvalues. You have the eigenvectors and your p1 p2, this is p1 p2 p3, and all other values will be given. Okay, so that's it. Thank you.